Okay, we're starting recording again. This is going to be for the second hour of Physics 1C for March 26th. And when we left, we were talking about this problem here, where I was wanting you guys to calculate the maximum power output of the battery, or to what value of the resistance, the external resistance R, leads to a maximum power output from the battery. And while we were gone, I wrote these two equations here to help you to think about how this works. We solved up here for the fact that the current in the system is equal to the EMF of the battery divided by the total resistance. And then we defined the output power of the battery to be this expression right here, IE times or minus I squared R. And our goal is to maximize this. And we want to maximize it related to this quantity, basically. We want to know the value of this that maximizes the power output. That's the idea, right? Leaving all of the variables the same, the value of the big R that maximizes the power output. Does anyone have any idea how you do that? And I should really be checking the chat here. If you guys are asking questions in the chat and someone notices and I don't answer, let me know. Doesn't look like it. Okay. Anyone have any ideas about how you would do that? How do you do this? Maximize. Where have you heard that word before? That is correct. Does everyone understand that? Anytime you see this word, okay, if you see the word maximize, optimize, minimize, you should immediately think derivative. Like, that's the first thing that your brain should do. Anytime a problem like this, whether it be in chemistry, physics, biology, economics, computer science, it doesn't matter what it is, this word maximize, it should instantly make you think take derivative. Because if you remember from your calculus courses, when you do these optimization problems, does that sound familiar to you guys? At least one person recognizes, but the rest of you guys, now that I say it, does that sound familiar to you? Sure. It's R, right? Because we're looking at the value of R that leads to the maximum power output. So you have to basically take the derivative with respect to capital R. And then what do you do with the derivative? You can't just take the derivative. It doesn't give you an answer, right? What do you do with the derivative? Yeah, you set it equal to 0 because the place where the derivative is 0 is the place where the function has a maximum, right? Derivative is equal to 0 here. That's a maximum, right? When the tangent line has a slope of 0, which is a horizontal line, that's where the derivative is 0, right? So then you set it to 0. And then what do you solve for? You solve for big R, right? You can do this symbolically if you want to, or you can do it using the numbers, whichever one you're more comfortable with. I would suggest trying to do it symbolically because it leads to kind of an interesting result. So now that you kind of know what to do you guys want like 10 minutes to try to give it a shot? Okay, as you guys are doing it, feel free to ask questions. Some people might need 10 minutes, dude. As you're doing it, feel free to ask questions, and you can talk to each other too. I mean, this is just like in a regular class. Like, you're all in voice together. And one of the things that we're missing from being able to go on campus is the ability to socialize with each other. And, that means the ability to eat lunch together, but it also means the ability to talk to each other about homework, right? And so one of the most important parts about education is, connecting with your peers and talking to each other, working in groups and all that kind of stuff. So here you are. You're in a big group chat. You're welcome to go to another channel if you want to talk to your friend about something, if you're too afraid to ask in a large channel. But ask questions. And if you have questions, just ask, talk. While you guys are in the stream, it's a really good idea to set your microphones to push to talk in Discord. If you don't know how to do that, I think I can show you. You go into click settings, and then you go to voice and video, and you click push to talk, and then you pick a button, and you have to push that button to talk. But while we're in here, I would ideally that's what you want to do, because someone just coughed openly into their mic, and yep. Since we're recording this stuff, we got to try to keep the quality kind of higher. So if you could switch to push to talk, you just gotta push a button to ask questions, but that's it. I think by default the system sets it to control or something like that, or tilde. Trying to figure out what, James? Yep. Yeah, it works fine. I didn't hear anyone yelling either, Alfie Sky. Oh, I heard that, yeah. Yes, this is the first time we did this with this class. I mean, my class yesterday was insane. There was someone that was like, I don't know, like constructing a house in the background while we were streaming. It was extremely loud, and they didn't know, huh? And they didn't know who. They couldn't figure out who it was, and so we had to the first 30 minutes of the stream was me trying to like individually move people out of the channel. But I don't know what other people think. Does that sound right to you guys? Oh, you got a plus minus? Well, little r, big R both can't be negative. You can't have negative resistance. Doesn't make any sense. That could be the right answer. I'm asking, did anybody else get the same answer? I'm assuming people need a little more time, so. that is the right answer. So I'll leave it for you to prove for yourself. This is again one of your homework problems. So but this is the strategy basically, right? You take this, you plug it into here, and you take your derivative with respect to. Sorry for the noise. I have to move these things apart real quick. Is that as far as that will go? Okay. So yeah, that's pretty much it. What you should be able to prove here is that the value of big R that maximizes the power output from the battery is when these two are exactly equal to each other. All right. So as you guys were doing that, I hope maybe some of you didn't quite finish it, and maybe you can take some time to finish it on your own. But do you have any questions about the process, about what you need to do? And feel free, don't be afraid to ask. I suspect that the vast majority of people did not finish this in the time that I gave you. I know that it can take quite a bit of time to do calculus problems, especially when maybe your calculus skills have lapsed a little bit. I know that when I took courses in grad school, I completely forgot all my calculus, and I had to relearn it over a period of a couple years, and so I was really slow. So that's why I was saying I'm sure this takes longer than 10 minutes. So if you weren't able to finish, that's okay. But if you do have questions about how to do it, now would be a good time to ask. So do you guys have any questions? Okay, if not, we will continue on then. The next topic that we have, should we go way back here? Oh, we just did power. So the rest of the class is going to be about Kirchhoffs laws then, actually. I do have one other thing I want to show you real quick here, though, before we move on, which is this diagram right here. Here, we'll just pull this up here. We're going to zoom in and just talk about it. So the phrase potential rise and potential drop is something that you're going to hear me say quite a bit. You're also going to hear it show up in your textbook, okay? So I believe this is the same circuit we were just talking about, right? 2 ohms, 4 ohms, 2 amps of current running through the circuit. Was that the same as ours? Yeah, 2 amps, 2 ohms, 4 ohms, right? Okay. So it's our same circuit, but this is drawn in a little bit different way. So what you have here, and I apologize for all these visual artifacts. I need to get a different quality PDF. This is just coming from the PDF for university physics, and for whatever reason you get these weird things happening here, but we'll just stop and look at what we have. There's a battery right here, 12 volts, ideal EMF source. The battery is the brown box, 2 ohms, and then 4 ohms. And what we're plotting on the bottom, this is a plot, right? This is voltage, and it's basically voltage versus like length along the circuit, you might say. But it's really just a diagram to represent voltage drops. So starting from the left side of the battery right here, you start off with 0 voltage, okay? But then as you go from the left side of the battery to the right side of the battery, the voltage jumps up. We call that a potential rise or a potential or a voltage rise. It jumps up as you go from this side of the battery to this side of the battery, from 0 volts on the low end to 12 volts on the high end. So now you're at 12 volts, right? And then we cruise along this segment of the wire. There's nothing there, okay? But then when we get to the 2 ohm resistor right here, it's going to use up some of the energy of our battery. So there's going to be a voltage drop. And the size of the voltage drop is equal to IR. Okay, this was where we had that equation. I mean, I'll write it again, down again over here to the right. Our equation says that you start off with some EMF, right? And then when you get to the resistor, you get a voltage drop that's I times little r. And then, when we get to our next resistor, so that would be 4 volt drop. This one's 4 ohms, and then you get a voltage drop back down here. So that's our next voltage drop minus IR. But then we're back to 0. So this one was plus 12, right? This one was minus 4. And this one would be minus 8. And of course, the sum of the voltage drops equal to 0. That's one of the Kirchhoffs laws, actually. But basically, every time you go through this resistor, you get this drop in voltage. And you get another drop in voltage. But then it kind of continues back around, and then you get a gain, and then a drop, you come back around, you get a gain, and a drop. So every time that there's a resistor or any other type of element within the circuit, because this doesn't just happen with resistors, there's other things that we're going to input in here later things called inductors, and then even capacitors. We can talk about voltage drops on those as well. But each element of the circuit is going to effectively use up some of the energy of your battery, and we call that a voltage drop. Okay, so this phrase you're going to hear me say over and over again is that things like this represent a voltage drop. Does that phrasing make sense to you guys? All right. So the next thing we want to do is to talk about Kirchhoffs laws. So this is going to be kind of a new section here. And we're going to talk about Kirchhoffs laws. These are extremely useful, although limited. Here, I want to use bigger ink than that. I don't like writing with such. Oh, that is big. I'm just zoomed out. We'll just make it bigger then. Okay, so we're going to be talking about Kirchhoffs laws. So this is spelled Kirchhoff, and it's either Kirchhoff or Kirchhoff. I always say Kirchhoff, but it's probably just because I don't have enough knowledge of how you're supposed to spell it. So Kirchhoffs laws. So there's two of them, okay? They are the loop rule and the junction rule, okay? So one of these is called let's do the loop rule first. So the loop rule basically says this: if I sum up all of the potential drops within a circuit, this is equal to 0. Okay? And I just showed you an example of that just a second ago. Okay? I'm going to look at one real quick application of this right here. Okay? So suppose we have a battery that has an EMF E. Okay? And we attach to this battery a resistor that has a resistance R. Okay? And we come back down to here. The loop rule says that if I start at some point in my circuit, let's say point right here, call that point A. If I then go around the circuit in a loop like this, it says that what I get when I go through here is a voltage drop that's equal to I times R. There is going to be a current flowing here, this, but it's negative. And then as I go back around to here, I gain energy, so plus E. And then the loop rule says that if I sum up the voltages, right, the voltage for this one, right, this is delta V on the resistor, plus delta V for the battery, you might say. This one's negative IR, this one's E, and they sum to 0 in a circuit like this. That's the loop rule. That's it. Okay? We're going to use that to solve problems. You'll see how useful it can be. So that's Kirchhoffs rule 1. And this is sometimes referred to like as, I think it's called like KCL in, is it KCL? No, it's not. It's KVL, I think. For K for Kirchhoff, V for voltage, and the L for loop or something like that. I think this is the expression they use in engineering textbooks, although I can't remember. I could be getting that wrong. The other rule is called the junction rule. Junction rule. And the junction rule says that the loop rule works around closed loops. The junction rule works at junctions, okay? And it says the sum of all currents flowing into a junction has to add to 0, okay? A really simple example of this would be like this. Suppose I have a circuit that's like this, and I have a branch in my circuit at some point, and I tell you that the currents flowing in my circuit in this segment are I1, and then here I2, and then here I3. The junction rule states that if I add all of the currents flowing into this junction, they have to sum to 0, okay? So the rule we use is incoming current is negative. Oh no, I usually use positive, don't I? Sorry. Is positive. And then outgoing current is negative. Okay? So the junction rule for this system right here would just be I1 minus I2 minus I3 is equal to 0. That's it. Those are Kirchhoffs laws. This one says that the sum of all voltage drops around a closed loop is 0. And this one says that the sum of all currents flowing into a junction has to add to 0 with this type of convention right here. Does that make sense? We're going to look at applications of this, of course. But most of the rest of class will probably be solving problems using these Kirchhoffs laws because it's like you have a whole homework set on these basically. And to when do I have it set right now that the next homework is due for your guys' class? I think I extended it last night. Do you guys know off the top of your head? Yeah, well, when we get to the next break, we'll talk about that. I just want to make sure that, just keep in mind, I will, go ahead. Okay, and then the next one's not due for like a week or so or something like that, right? Yeah, I also extended the DC circuit one, so I just want to make sure because there's going to be one topic, which is RT circuits we probably won't get to today because we'll spend a lot of time doing these kind of problems. So these are the rules, and we can talk about why they're true, first of all. They're both an expression of energy conservation, okay? Let's talk about the, actually, junction rule first. Let's do this one. This is an expression of conservation of charge. So conservation of charge is the idea that you can't create or destroy charges, that if you have any charge that flows in, like this way, has to also split up and flow out this way, right? So you can't have charges building up here, so any charge that flows in here also has to flow out here. That's conservation of charge. The loop rule, I have to be careful about how I say this since this is going to be posted on the internet. I'll be subject to people flaming me if I'm wrong. It's basically the idea that when you go from all the way around a loop, that if you were to measure the potential difference between like this point and this point, you would get, here, let's call this B. If I measure the potential difference between this point and this point, the answer is going to be E, or it's going to be IR, right? That's actually what we did in the previous problem, right? Does that make sense to you guys? If I attach a voltmeter between these 2 points, the voltmeter is either going to read E if E is 12 volts, or it's going to read IR, and they'll both be the same. It'll be like 12 volts, basically, right? So if I measure the potential difference between a point and itself, though, like we put 2 points right next to each other, right? So we call this B prime. The answer is going to be 0. I know we've only done one lab in this class, and that's really unfortunate. But remember in the lab we did that you guys connected the black piece of your voltmeter to the negative terminal on your system, right? And then you were measuring with the red piece of the multimeter different voltage values, and you use that to plot out the equipotentials. You guys know what I'm talking about? If you ever took the red thing and you put it on the same connection as the black thing, you would get 0 volts, right? Did you guys follow what I was saying? Like if I took a multimeter and I connected it to this point and I connected it to this point, the voltmeter would read 0. Does that make sense? Because you're basically measuring the potential difference between a point and the point that's right next to it where there's nothing in between. Now, if there's a battery in here, you're going to get something, right? But you're going to get 0 when you measure the potential difference between 2 points, right? So that potential that you're defining there can either be the potential between these 2 points or all the way around the loop, right? From this way, this way, this way, this way. You see what I mean? So both have to give you the same answer. And that's at least the way I think about it. Okay. Do these 2 laws make some kind of sense to you guys? To where we can start using them to solve problems? You guys want to ask questions at all, or? Okay, so there are some rules. They're right here. I'm gonna write them out, and then I'm gonna drag this thing down for you to show what it is. There are some rules about how we define these voltage drops right here. Okay, and we call these the sign conventions. Let me just zoom out just a little bit so I can keep this on the screen, and we'll talk about the sign conventions for Kirchhoffs laws. This is kind of tricky, but pretty easy to understand once you've done this a little bit. So let's get black. The sign conventions for the loop rule. Let's put these up here. That way we can refer back to them pretty easily while we're doing problems. So there's a couple ways that this can occur here. So I can have, for example, a battery that's aligned. Let's do the first one like this. Undo. I need to just zoom in for this part because it's going to make it a lot easier to do it. Oh, why can't I go farther over? I thought I could go infinitely over. Oh, does it just like slowly give me space? I don't know. So these are the sign conventions. So I can have a connection where I have the negative terminal of the battery here and the positive terminal of the battery here. And we say that we have an EMF E, okay? This is the negative side, this is the positive side. And then I'm going to label this side to be A, this side to be B. And then we're going to say, suppose that we have a system like this where the current is flowing in this direction. Okay, so that's the direction of the current. Okay? The delta V for this one is going to be equal to positive E. You're going to gain energy when you go from the negative side of the battery to the positive side of the battery. By comparison, and I think the book would call this like VBA or something like this, but delta V as you go from here to here is going to be positive E. I think the book would use the expression probably the potential of point B relative to point A. I think that's their notation, but I don't like their notation, so I don't really use it very often. We can just check real quick. They don't even use it when they describe this. Okay. So the other possibility would be that you have the same exact thing, except you reverse the direction of the current. Or you just reverse the direction of the battery would be the same thing, I guess, right? So suppose we have a battery, and it's aligned like this. Oh, I just realized something. I did something completely wrong. I just lied to you guys completely. Oops. Sorry. Probably didn't need to erase all that, but it's fine. Won't let me go back that far. I lied to you. That is not exactly right. So same situation. We have battery, negative, positive. Okay? And the reason why you need the A and B here, I now realized, is because this is going to be the direction of the loop that you're going around. So this is going to be your loop direction. Is that direction, okay? Then this is going to give you delta V, assuming this is an EMF of E equal to positive E. And our loop basically is going to always go from A to B here, is what we're going to do. Okay. So in order to create the same thing but switch it, we'll have point A right here, and then we'll just change the direction of the battery. So the battery is going to go plus here, minus here, over to here. And if your loop direction now is the same as above, okay, so your loop direction again is in that direction. We'll continue to make the loop direction this way. Then, just in case, I'll draw this. This is going to give you delta V equal to negative E, okay, because you're going from the high point of potential to the low point of potential, all right? The other possibilities are with a resistor. So now we say, suppose I have point A right here, and then I draw a resistor. Say it has resistance R. This is point B, and now is where we have to identify the current. This is why I was kind of getting ahead of myself, I apologize. Now suppose the current flows this way. And remember I said before that when you go across a resistor, the resistor effectively drops the voltage. Okay, so B is going to be at a lower potential than A, which means delta V in this case is going to be equal to negative I times R. And again, you're assuming here that the loop direction is this way. Notice that when the loop direction is the same as the current direction, you get a negative sign, okay? It's effectively like you're traveling downstream, okay? You're traveling downstream, so that this point is a lower potential relative to point A. Does that make any sense to you guys? If you think about it in terms of energy, it's like if you wanted to go from B to A, you'd have to swim upstream, right? So you'd be moving from a place of low potential to high potential. But if you go from A to B, you're going downstream, or like rolling down a hill, right? So as a result, you basically lose energy, yeah? Every charge that passes through here is going from a high place of electric energy to a low place of electric energy. That's why it's negative. It's also why we call this voltage drops. Okay. I'll pause for a second. Do you guys have any questions? The final possibility, no questions at all? How exciting. All right, so the current goes this way. Loop is in the same direction now. So now when your loop direction is opposite to your current direction, you end up getting delta V is equal to positive R. Positive IR. Oops. Equal sign plus IR. Okay, so those are our rules. And they're summarized. I draw them out like that because I feel like if I just plop this thing in here, you're not going to understand. Not like my explanation's all that great or anything like that, but... Okay, I don't understand why I can't go farther right. I'm pretty new to this OneNote software, but it's like sometimes it allows me to do it and not. I don't know. So if we pop the thing right here, and we just expand it so you can see it a little better. There you go. So those, get them all together on the screen, represent our loop rules. Positive E, if you go from minus to plus. Negative E, so travel is like loop direction. If you go from, so basically they're saying travel this way, you get positive E. You travel this way, you get negative E. If you travel opposite to the direction of the current, you get plus IR. And if you travel in the same direction as the current, you get negative IR. And those are the sign conventions combined with, you know, Kirchhoffs laws. So if you guys don't have any questions, we're going to start looking at problems and how we use these to solve them. Starting with this one. Okay. We're going to do two types of problems here, actually. I realize this one's a little different, actually. Maybe we just do this one last. We just immediately do the loop rule one, because what you're going to find from doing your homework... Did I completely lose that thing? Oh, or maybe it's just in the paste? Yeah, okay. Let's do this one instead. Oh, no. Click. Paste. This problem. This is a good loop rule problem. So 26.28 is the one we're going to do right here. It says, in the circuit shown, in this picture here, where you have a battery here, and then all these resistors, the current in each, we want to find the current in each branch of the circuit, the potential difference VAB of point A relative to point B. Okay, and then this is a different problem with the same picture, but we're just going to do 28. Okay, I think this is actually a homework problem you guys have. So, how do we do this? So we're going to use Kirchhoffs rules to handle this circuit. And before we can really do that, we need to really like kind of draw a circuit ourselves so we can, because this is just kind of too small right here. I guess we can make it big enough, but there's just very little room to write. So we're going to redraw the circuit. It's not going to look super great, but we'll try to do it with some boxes or something so it can kind of look a little bit better. So we've got one big box here. And then within that box, we need a line. It goes from here to here. And then that line gets broken up a little bit because we've got a resistor here. We've got a battery here. Got another resistor right here. Then we've got resistor, battery, another resistor, and a resistor out here. Okay. So let's go ahead and draw little squiggly lines for the resistors. Maybe we use red or something. So our resistors here are one here, another one here, and we know the values. This one is 10. Gotta write with a little bit thicker pen for that part. So this one's 10. This one's 4, 3, 2, we've got our batteries, with the batteries in blue. So our batteries are oriented. The orientation of the batteries matters. So this is going to be positive and minus with an EMF of 10 volts. And then this one is same direction, plus, minus. This one's 5 volts. And that's our circuit. And our goal here is to find the current in each branch, okay? So the first thing you have to do when we look at circuits like this is you need to label the direction of currents. It makes absolutely no difference how you do this, but the important thing to know is that anytime you see a junction, you're going to have the current split. So what I'm going to do is I'm going to define the current that's flowing in the upper branch right here, and it's going to flow all the way through there to there. We're going to call that one to be I1. Right? So we're just going to call the current that's flowing in the upper segment of the circuit, we're calling that one I1. So this is I1, this is going to be I1, and this is going to be I1. The current that's flowing into the middle portion of the circuit here, I'm going to call I2. I literally have no idea what directions these go, okay? I'm just picking a direction. It makes no difference what direction you pick, okay? In fact, I'm virtually certain one of these is going to be opposite. Finally, in the outer segment of the circuit here, all the way around here, we're going to define that current to be I3. Okay, so I3 goes between this point and this point, and then I1 goes up to here. Oh no, this is where on for YouTube at least. So I3 goes from here down to here, and then this way, and then I1 goes from here up to here, down to here, and then I2 is just in the middle branch of the circuit. Okay, and our goal here is to calculate what those currents are. So the next step of what we're going to do here is we are going to basically apply Kirchhoffs rules. The first thing we're going to do is the junction rule. And we'll just do it for this junction right here. And maybe to make it really clear, this is I1, this is I1, this is I3. The junction rule for this point right here, right? The junction rule says I have to sum up all the currents flowing into my junction, and they have to add to 0. So I've got I3 coming in. That's going to be positive. Maybe we use a different color for the work that we're doing. So we have oh no. I'm so far zoomed out, it has to be thick. Okay, so we have, at this junction, we have I3 coming in. So that's I3 plus I1 is going out and I2 is going out. So it's going to be negative I1 and then negative I2. And those should all add to 0. That's one of our equations. Does anyone have any questions about that? It's a pretty easy rule to use. Incoming current positive, outgoing current negative. The third step in doing these kind of problems is we need to draw our loops, okay? So let's use kind of a different color for that as well. Let's use blue. You choose the kind of loops you want to draw, and so we're going to draw for 3 different things here. So this is going to be loop 1. This one is going to be loop 2. So loop 1 is the bottom section, loop 2 is the top section. Can anyone think of another loop that I could draw in here? Yeah, that's right. I don't know if I can draw that on here very well, but maybe we'll use a different color and say that this could be our other loop. Leave it in kind of light because the picture's starting to get pretty junked up now. So this, all the way around the entire circuit, that's going to be loop 3. And now we want to use Kirchhoffs rules, right? want to write down equations for each of our loops, right? So let's do it. So loop 1 is in blue, right? So we'll do the ink in blue too. Okay, so for loop 1, maybe I can write this over here, I guess. Loop 1. There's our rules up there. Kind of hard to see. Okay, there's our rules. Loop 1. Let's pick a point to start, okay? So let's start like right here. Going around like that. What do I write down for the first resistor? Well, if we're traveling in that direction and the current's going in the same direction, we need to write down something like I3. Let's get this closer so I can organize. We need to write something like I3, which is an unknown, multiplied by the resistance, which is 10. And then according to our rules up here, can you guys tell me, should it be positive or should it be negative? Are we going in the same direction or the opposite direction of the current? Negative, that's right. So this is going to be negative. We go around in a circle right here. We're staying in this bottom loop, right? So we get to this one. What do I write down for this one? For this resistor? What's the current flowing through the 1 ohm resistor? What's the current flow through the 1 ohm resistor? Negative I2. Do you guys all understand that? So it's going to be minus I2 multiplied by the resistance, which is 1 ohm. So then times 1 ohm. Now we have a battery. What do I write down for the battery? Is it going to be positive or negative on the battery we write down now? Okay, because you're going against the battery. You're going in this direction, so you're going positive to negative, right? So if you go positive to negative, it's like going this way, plus minus. Okay, so we're going to write minus 5 volts. God, this really is not the most ideal. So 5 volts. As soon as I get to the edge of the screen, it becomes extremely difficult for me to write because I have nowhere to rest my hand. And then we're still not done. We have one more piece, which is this one right here. What am I going to write down for that one? Sorry, this one right here. What am I going to write down for this one? 4 ohms. Plus or minus 4I2, right? Okay, minus because we're going in the same direction as the current. That's right. So I2 and then 4 ohms. And all of this should be equal to 0 because that is what the Kirchhoff rules tell us. And I'm going to simplify this just a little bit here so it doesn't look so nasty. So let's rearrange this in the following sense. I'm going to order, so we have negative 2I2 and negative 4I2, right? So that's going to be negative 5I2. Then we have minus 10I3. I'm dropping the ohms things. And I'm just going to move all of the voltage stuff to the right-hand side. So I'm going to say this equals negative 5 volts. Okay. That's our equation for loop 1. Anyone got any questions about that? Now we're going to do loop 2. So loop 2, let's say we start, here, let's just start up here for loop 2. We're going this way, right? I don't know, all these extra resistors make this awkward. Let's start here for loop 2. So the current up here, I1 goes this way. So I'm going to write down what for this one? For the 2. This one right here, what are we writing down? We're going around the loop like this. We're looking at the upper loop now. What do I write down for the 2 ohm resistor? Yeah, so I'm just going to write 2I1, if that's cool with you guys. Understanding this 2 is in ohms. The battery, what do we put for that? Plus or minus? we're traveling in this direction, right? And that corresponds to this. So this one's going to be minus 10. Remember, you're going from high terminal to low terminal, right? The change is that you're losing voltage, right? This is the lower terminal voltage. This is the higher terminal voltage. You go from here to here, you lose 10 volts. 3I1 is going to be negative because you're going in the same direction. We swing down to here. We're going against the current now with I2. So what do I write down for this one? What do I write down for the 4 ohm resistor now? Plus 4, because we're going upstream, right? We're going to a position of higher potential. And we get to the 5-volt battery. Now we're going, the loop is this way, the current is this way, but the current direction doesn't matter for the battery. And so we end up getting plus 5 volts here. And we still have one less thing right here, which is this 1 ohm resistor. And that 1 ohm resistor is going to be also plus 1 I2. And I'll just pause for a second. Do any of those terms make sense to you guys? I'll use the mouse because on YouTube it doesn't pick up the pointer. So we started from this point. We said going in the same direction as the current through this, we get negative 2I1. It's a voltage drop. Going from here to here, we're going from the plus to the minus. When we go from plus to minus, like this one, you get negative 10. Okay. When we get to this one, it's negative 3I1. We get to here, in the branch between this point and this point, the current is flowing to the right, but our loop direction is this way. So if we're going that way, from this point to this point, we're going upstream, so we get plus 4I2, right? That's this one right here. When you travel opposite to the direction of the current, you're going upstream. You get plus 4I2. And then going to here, we're going from negative to positive, so we get plus 5. And the final piece is this one right here, which is going to be plus 1I2, because I2 is going that way. And then, we're back to the same point again. There's nothing between here and here. Yeah, I think that's right. This should be negative, right? That's what you're saying? That's right, for YouTube. Yeah, this one should have been negative right here. Definitely. I didn't see that. I'm really uncomfortable with the way I have to stream this, so Okay, so let's see. This one, yes, thank you very much for noticing that. Okay, this one should be negative. I really appreciate that. Which means this has to be positive. Thank you very much for noticing that. I appreciate that. Right on. We can simplify. Are there any other questions? So negative 5I1 plus 5I2 and then we've got 5 minus 10, which is negative 5. So when I add that to the right-hand side, it'll become positive 5 volts. So there's loop 2. And what I would like for you guys to do now is to try to do loop 3 for yourselves. And we'll take a break because it's 4 o'clock. But I want you guys to try to do loop 3 for yourself. During that break, we'll have a 15-minute break. We'll start again at 4:15. That should be enough time to step up, walk away from the computer, and also come back and to try to do what loop 3 is going to be. What color do you use for loop 3? Is like lavender. The one I used? Try to write the equation for loop 3, and we'll start again at 4:15.